Hello, and this is our third lesson of the week on reciprocal trig, and in this lesson we're going to focus on proof. Now, proof is one of those exciting things in maths where you feel like you might go around in circles for a couple of hours, but you will get there in the end. And the important thing to remember is the more you practice, the more these skills will become second nature and the more confidence you'll have with them. You may end up starting a question over and over and over again, but don't let that get you down. You have to just keep trying, and if you think you're getting nowhere, start the question again. Once you've done enough of those questions, you will you'll start to get them more quickly. So here's the kind of question I'm talking about. We need to prove that cot theta multiplied by cosec theta, all divided by sec squared theta plus cosec squared theta, is identical to cos cubed theta. Now the key word here is prove. And proof in maths is unlike proof in any other subject. We don't just accept a shed load of evidence to prove something. We have to show beyond any doubt that this thing is absolutely true. And in this, we use our trig identities to help us. So the first thing I'm going to do is I'm going to nominate a side of my identity here that I'm going to work on. It makes sense to work on the side that has the most stuff in it. Right? The most stuff means you can do more with it. So I'm going to start working on the left-hand side, which I'm going to denote by writing LHS, and I want you to get into that habit as well. So I'm starting on the left-hand side, and I'm going to rewrite this using stuff that I know, anything. And at this point, I don't really have any idea where this question is going to take me, but I know that I can swap cot for something, cosec for something, sec squared for something, and cosec squared for something. And then I just need to see what happens. So I'm going to swap cot. Now I could swap cot for 1 over tan, but I can see from the rest of the question that we've got cosec here, so sine is involved, sec here, so cosine is involved, and another cosec here. So I think it makes sense to swap out cot, not for 1 over tan, but for cos theta over sine theta. So that's my cot, okay? Cos theta over sine theta. I'm then going to multiply that by 1 over sine theta, and I'm already looking at this thinking I can combine these two things into a single fraction, but I'll do that in the next step. So then I'm going to have that over, because that's my fraction line here, and just a note, kind of an aside really, is you will find yourself doing fractions over fractions. That's fine, okay? We do simplify them down at the end, so don't worry about using it during your working. Okay, sec squared. I do know an identity for sec squared that we looked at yesterday. But actually, I'm thinking I'm going to stick with 1 over cos squared. And the reason for that is my identity for sec squared uses tan squared, whereas my identity for cosec squared uses cot squared. So I suppose I could use those. I might be able to combine those. But for me, it makes sense to just stick with the basics. So I've got cos over sine multiplied by 1 over sine, that's my numerator, 1 over cos squared plus 1 over sine squared, that's my denominator. So let's go and do a little bit more work here. Let's say multiply these two fractions together, because that's what we have to do. Cot times cosec is this times this. Let's do that. All right, multiply the two fractions on the top. We get cos theta times 1 over sine squared theta. Okay, so that's my numerator. My denominator, well, I'm going to add two fractions, so I need a common denominator. So I'm going to say, how do I turn this fraction into a common denominator with this fraction? Multiply top and bottom by sine squared theta. So I end up with sine squared theta over sine squared theta cos squared theta, because cos squared theta times sine squared theta is my common denominator, plus, what do I have to multiply sine squared to make it into sine squared cos squared? I have to multiply top and bottom by cos squared. So I've still got some horrendous fractions going on here, but that's not a problem. Next line of working then is going to be still my cos theta over sine squared theta on the top. But this time I'm going to add these two fractions together. So when I add the two fractions together, I get sine squared theta plus cos squared theta all over the same denominator, sine squared theta cos squared theta. So now, again, looking at what we've got to work with, I'm going to concentrate on the denominator for a second. Sine squared plus cos squared is 1. So I end up with cos theta over sine squared theta all over 1 over sine squared theta cos squared theta. Now, at this point, I can't really shrink these down anymore. I've combined the numerator and denominators both into a single fraction. So I'm going to remember now that if I'm dividing by a fraction, I am multiplying by its reciprocal. So I've got cos theta over sine squared theta, that's my numerator, multiplied by the reciprocal of the denominator. So we've got sine squared theta cos squared theta over 1. And combining these two fractions together, I end up with sine squared theta cos cubed theta, okay? Cos multiplied by cos squared is cos cubed, and then sine squared theta is still there. And that's all divided by sine squared theta multiplied by 1. And at this point, I can see that sine squared theta on the top and sine squared theta on the bottom cancel each other out. And so I end up with cos cubed theta. And I finish my proof as required, because cos cubed theta was the right-hand side of my identity. Now, it's important to note there's always, or usually I should say, more than one way of doing these proofs. So there's no kind of right answer or wrong answer. I mean, there is, in that you have to prove that one thing is the other thing, but there's no right way or wrong way of doing it, really. So that's my proof. Just to talk through it again, I swap out what I've got for what I know it's equal to. So cos was cos over sine, cosec was 1 over sine, sec squared was 1 over cos squared, and cosec squared was 1 over sine squared. Once I've done that, I'm just combining fractions wherever possible, all right? Putting them together as 1. If they don't have a common denominator, like these two when they had to for an addition, you turn them into fractions that do have common denominators. Then you combine them. So I needed to combine my fractions on top and bottom. And once I'd done that, you know, you're always on the lookout for things that you can make simpler. And then once I'd done that, I could see sine squared plus cos squared there. Now I know that that's 1. So I can then simplify down again. And once I've simplified the fractions as far as I can go, I can then say, well, it's the numerator multiplied by the reciprocal, the denominator, and then that led me to this lovely result here where sine squared cancels with sine squared. And it happens quite a lot, and there's a nice sense of satisfaction you get when you get to the end of one of these questions. So part B of the question says, hence explain why this equation equal to 8 has no solutions. So the word hence means use what you've just done. So what we're saying is because the big equation was identical to cos cubed theta, the equation we're trying to solve is that cos cubed theta equals 8, which means that cos theta is the cube root of 8, which means that cos theta is 2. And we know from our cosine graph, it only exists between 1 and minus 1. So for cos theta to equal 2 is impossible. So that's one type of proof. And you'll get a lot of practice at that today. And for those working remotely, you just have to take a picture of any questions you've got, send them to me on Teams, and I will reply as soon as I can. Now there's another type of proof, okay? And it's this. So let's read the question. Given that tan A equals minus 5 over 12 and that angle A is obtuse, find the angles of, find the exact values of sec A and sine A. So here's what we do. Whenever you're given a question that says something about and the angle is obtuse or it's reflex or it's acute, there's always a kind of standard process. We're going to use one of our identities where we square things. Now, what do I mean by that? So here we've got tan A is minus 5 over 12. And we want to know something about sec A. So do we know an identity that links tan with sec? We sure do. We know that tan squared, let's use A because that's in the question. So tan squared A, tan squared A plus 1 is sec squared A. All right, so let's do that. Let's actually work out then what's tan squared A. Well, tan squared A is just this squared, so we've got 25 over 144. So 25 over 144 plus 1 is sec squared A. So you can see how we're using values here to work out. And you can probably see all we're going to do is add these and then square root. So 25 over 144 plus 1 gives us 169 over 144. And so sec A is plus or minus 1312. Right? Important to remember that when we're square rooting, we need the plus or minus. Now, our answer isn't plus or minus 13 over 12. It's either plus or it's minus. So in order to work out which it is, we're going to remember then that that means cos A is going to be plus or minus 12 over 13. Right? If sec A is 13 over 12, then cos A is 12 over 13. And I'm going to think about the cos graph for a second. There's my cos graph. Some of the key values, I know that that's 90. I know that here, down the middle here, is 180. Now, this is where the obtuse part comes in. If the angle is obtuse, it means that A, the angle, has to be between 90 and 180. Now look at the graph. For the whole of that limit from 90 to 180, the cos graph is below the axis. And if it's below the axis, it means that any of the y values that you get from it are negative. So that means, using that kind of knowledge and intuition, that means that sec A is going to be our negative 1312. All right, and just to repeat that, we use the identity to find out sec squared. We square rooted, remembering we had plus or minus. We needed to choose one or the other. So a quick sketch of the cosine graph, because cosine is 1 over sec, or sec is 1 over cosine. And we saw that where A is obtuse, i.e. between 90 and 180, as specified in the question, the cos graph is negative. And if the cos graph is negative, then 1 over the cos graph is also going to be negative. And so the sec graph is negative. So let's try the same thing then for B to work out what sine A is. There's numerous ways of doing this. There are other ways of doing part A, but I'm going to stick to my squares, okay? And I'm going to say then that I'm going to use sine squared A plus cos squared A is 1, okay? Sticking with the squares here. We're going to go to here, right? Cos A is plus or minus 12 over 13, so we've got sine squared A plus cos squared, so the square of 12 over 13 is 144 over 169. Okay, just square the top and square the bottom of 12 over 13. So sine squared A is 1 minus this, and so we get 25 over 169. And so sine A is going to be plus or minus 5 over 13. And we have that same predicament, plus or minus. So we just need to draw a quick sketch. And we're interested this time in our sine graph between 90 degrees and 180 degrees. And we can see here the graph of sine is above the axis between 90 and 180. Again, that's important because it says obtuse in the question. A has to be obtuse. It has to be between 90 and 180. So it's above the axis here. That means that our sine is going to be positive. Now, when I was talking about other ways of doing this question. You can use Pythagoras theorem. The initial information we were given in the question was that tan A is minus 5 over 12. So we can think of a right angled triangle with 5 and 12, okay, opposite over adjacent. We can very quickly work out that the hypotenuse is 13. So, you know, we can get just from there the fact that cos of A is going to be 12 over 13 here. And we can get the fact that sine of A is going to be 5 over 13. What we don't get from there is the plus or minus aspect. So if you are going to use this right angled triangle method because it's simpler, remember it's not as simple as just writing sine A is 5 over 13. The decision has to be made if it's plus or minus. And that's why I prefer using my squared identities, because that makes it very clear when I square root that I've got to be mindful of the plus or minus. And that reminds me to draw the graph, which will then help me to decide if it is plus or minus. So there you have it, 2 types of proof using reciprocal trig ratios. It's going to take practice, and it may not click completely in this one lesson, but we will come back to this over and over again, just like we did with trig equations, until we are a lot more confident. In the meantime, if you're working remotely, put your questions in the chat and I'll respond as quickly as I can. Thanks.